Dear students, welcome to the next lecture of Inorganic Chemistry. In this lecture, we shall discuss about the group 16 elements, that is the oxygen family. The elements of this group are oxygen, sulfur, selenium, tellurium, polonium, and livermorium. The elements of group 16 are also known as chalcogens, meaning ore-forming elements. This is because a large number of elements are found in their sulfide or oxide ore forms. The general electronic configuration of group 16 elements is Ns2Np4. Oxygen with atomic number 8 has an electronic configuration of 1s2, 2s2, 2p4. Sulfur with the electronic configuration of neon plus 3s2, 3p4 and so on. The atomic size of group 16 elements increases as we move down the group. This is because as we move down the group, more and more shells are added to the atoms. Oxygen has an atomic radius of 66 picometer, sulfur 104, selenium 117, tellurium 137, polonium 146 picometer. If we observe the trend, it is found that there is a sharp increase from oxygen to sulfur, and the increase is not so pronounced as we move from sulfur to polonium. This is because of the poor shielding effect of N-1 d electrons in the case of selenium and tellurium, and -1 d electrons and N-2 f electrons in the case of polonium. The same trend was observed in the case of the atomic size of group 15 elements, which we have already discussed in previous lectures. As we go down the group, the ionization energy decreases. So oxygen, the smallest member, has the highest ionization energy, and as the size of the atom increases, the ionization energy decreases, and hence the metallic character increases as we move down the group. The decrease in ionization energy from oxygen to sulfur is very high, and from sulfur to polonium, the decrease is not much pronounced. This trend can also be explained on the basis of poor shielding effect of d and f electrons. Usually, as we move across a period, the ionization energy increases. But if we compare the ionization energy of group 16 and group 15 elements, group 15 elements show higher ionization energy compared to group 16 elements. This is because of the extra stability of the half-filled orbitals in the case of group 15 elements. For example, if we consider oxygen and nitrogen, nitrogen has a higher ionization energy because of the extra stability of the half-filled orbitals. If we observe the electronegativity trend, oxygen is highly electronegative, and as we move down the group, the electronegativity decreases. Oxygen has an electronegativity value of 3.5, sulfur 2.5, selenium 2.4, tellurium 2.1, and finally polonium 2.0. The decrease from oxygen to sulfur is more pronounced, and thereafter the electronegativity do not vary very much. This can also be explained on the basis of the poor shielding effect of N-1 d electrons and N-2 f electrons in the case of higher elements. Group 16 elements show various oxidation states. Oxygen can exist in -2, -1, +1 and +2 oxidation states. Sulfur in -2, +2, +4 and +6 oxidation state. Same as with selenium and tellurium. And polonium exists in positive oxidation states +2 and +4. We have already discussed about inert pair effect in the case of group 15 elements. The non-participation of the s electrons in bonding due to the high energy needed for unpairing them is called the inert pair effect, and this is due to the poor shielding effect of d and f orbitals, and hence the effective nuclear charge on the outermost s electrons will be greater. Because of inert pair effect, selenium, tellurium and polonium have a strong tendency to exist in +4 oxidation state than +6. Thus, selenium-6, tellurium-6 and polonium-6 are strong oxidizing agent so that they get reduced themselves to +4 oxidation state. Coming to the physical state of group 16 elements, oxygen is a diatomic gas and all other elements are solids at room temperature. In oxygen, in O2 molecule, there is one sigma bond and one pi bond. The bonding is shown in the figure. In O2 molecule, there is an effective p-pi bonding. And this p-pi bonding is not much effective in the case of higher members, sulfur, selenium, tellurium. And hence these elements do not have a tendency to exist in diatomic state. Sulfur exists as S8 molecule. The puckered ring structure of S8 molecule is shown in the figure. The melting point and boiling point of elements of group 16 increases as we move down the group. Among group 16 elements, oxygen has the lowest melting and boiling points. The melting point of oxygen is -218 degrees Celsius and boiling point is -163 degrees Celsius. This is because oxygen exists as gas at room temperature and all others are solids. Oxygen is a diatomic molecule, whereas other elements exist as polyatomic molecules. The occurrence of an element in more than one physical shape is called allotropy. Group 16 elements show allotropy. Oxygen has two forms, O2 and O3. O3 is called ozone. Sulfur exists in rhombic, monoclinic and plastic forms. Selenium in rhombic, monoclinic and gray. Tellurium also exists in crystalline and amorphous forms. The allotropes of sulfur, monoclinic, rhombic and plastic sulfur are shown here. The three forms of selenium, black, red and grey selenium, are shown in the figure. Next is the binary hydrides of group 16 elements, H2O, H2S, H2SE, H2TE and H2PO. H2O is a liquid, whereas others are gases. H2S, H2SE and H2TE are poisonous with unpleasant odors. As polonium is a radioactive element, the properties of H2PO are not well known. Coming to the structure of the hydride, the group 16 element is sp3 hybridized with 2 lone pairs and 2 bond pairs. It has a bend structure as shown in the figure. The bond angle varies from the tetrahedral angle because of the presence of lone pair. We know that the lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. The bond angles of the hydrides are, for water it is 104.5 degree, for H2S it is 92.1. As we move down the group, the bond angle decreases. This is because as we move down the group, the atomic size increases and electronegativity decreases, and hence the bond pair repulsion decreases. The boiling points of hydrides are shown in the table, of which H2O shows an anomalous boiling point. Comparing the other three hydrides, H2S, H2SE and H2TE, as we move down the group, the molecular size increases, hence the van der Waals forces increases and boiling point increases. The boiling point of water is 100 degrees Celsius, which is an anomalous value compared to the other elements of group 16. This can be explained on the basis of electronegativity difference of oxygen and hydrogen. Oxygen has an electronegativity of 3.5 and hydrogen 2.1, and because of this the OH bond is highly polar and intermolecular hydrogen bonding is possible in the case of water molecule. And because of this intermolecular hydrogen bonding in water, it has a high boiling point compared to other hydrides of group 16 elements.